and those that are coming in come in and then start. So what I thought I'd do this afternoon, David a little earlier talked about my experience and background in terms of linking subsurface geoscience to surface geology. So I wanted to do a little bit of that this afternoon with you, to talk about the new insights from integrating some of the subsurface imaging that is now possible and achievable with field exposures. So what I'm going to do is what I hope to be able to do is to show how the development of some of the geophysical methods over the last 50 years have enabled this high fidelity imaging of the subsurface. And whilst this has been the primary preserve of oil and gas companies, of course, exploration companies looking in the subsurface, the data affords an amazing opportunity for academics and others, this unparalleled opportunity to investigate Earth processes using such techniques, sort of data falling off the back of the lorry. So I often go along at conferences with my little shopping trolley, and with the hope that people are going to put data into that shopping trolley to enable us to look at the subsurface. And what I want to do here is to show how some of that of these data allow one to extend our understanding of tectonic and stratigraphic processes in northwestern Europe beyond our coasts and beneath our feet. So it's this improvement of seismic acquisition, particularly that's actually happened over the last 5 or 10 years with what's called broadband seismic and the like, to allow you to look at different frequencies of data, that's led to the higher quality imaging of the subsurface. This gives us the opportunity to describe, to interpret, to understand some of those processes, but also importantly to quantify them, particularly if we have biostratigraphic or other dating control. One byproduct, and this is the bit I'm going to concentrate on during the course of this short talk, is to enable field exposures which have proved to be spectacular, yes, enigmatic definitely, to be placed in a proper regional or structural context. And what I thought I would do, carrying on partly the Durham theme that seems to be running through the course of the afternoon, is to use 3 examples, the first of which is going to be the Zechsteiner County Durham and some of the fantastic work that was done, of course, onshore, looking at those sequences by educators at Newcastle, Durham and elsewhere. Secondly, I'm going to look at so-called alpine deformation of the Wessex Basin. Is it truly alpine? Is there something else driving it? What does it look like? I also want to use subsurface data combined with William Smith's map to effectively document the uplift and tilt of the British Isles and to see some of the effects of that and consequences for society and for the economic future of the country. So let's start with the Zechstein. This is a diagram which is simply a cross-section conceptualized to show the build-out of the Zechstein carbonate and evaporite system, which occurred in a series of cycles, Z1 to Z5, in northeastern England. This Zechstein rimming shelf, platform and shelf, built out into the basin in a highly evaporitic sense. Now, we can use subsurface data, wells from 4 boreholes in this particular instance, to highlight the same geometry that was described onshore by Dennis Smith and others so beautifully in northeastern England, exists offshore. So these are the lithological logs, the well logs, petrophysics as well, and what we're seeing here is the build out of a carbonate and anhydrite platform and then evaporites occurring further outboard. Now if we look at the overall system, we have a platform, a slope and then a basin. Now, what we can do in the subsurface is look at the rock cuttings, of course, the cores that are taken from this to get some ground truth to the electrical well logs. But something else is highlighted here, and this is the main boundary between the thick halite, evaporites here, and the anhydrite and carbonates beneath. And there is a major velocity and density contrast between these different rock types. What that leads to is the potential for there to be an acoustic impedance contrast between these. So potentially, what was mapped in the field should be identified, could be identified, has the potential to be anyway, in the subsurface. So here is that same cross-section with the wells, This is an artificial synthetic seismogram which highlights what one would anticipate, one would expect to see in the subsurface. Now let's factor in the new geophysical acquisition and the imaging. And lo and behold, through here, this is one of those wells, this surface coming down here, which might otherwise be ignored or overlooked, happens to be the boundary between the anhydrite and the halite in the subsurface. What does this enable us to do? It enables us, for the first time, to start to image a paleogeography from the Upper Permian in the subsurface at 2 or 3 kilometers depth. Here's another example. There are changes in acoustic impedance properties with this bright pod in here, another bright pod, well in here, that can also be mapped. And this is a map looking down onto two of those pods, one here and one here. You can see that they're sort of circular to elliptical in shape, thicker in the center. We combine all this information, and what we can do is produce a three-dimensional paleogeography of the subsurface. Here is the shelf margin with its promontories and embayments all the way along its length. In here, these ovoid and circular depressions are the saline pods, just like we see on the Trucial coast today. This is the paleogeography. It is modified from work done onshore, but now we can extend that work into the subsurface. So here is the platform margin with its promontories and embayments. Even seeing off-platform remnants, material, debris cones and the like being shared, and back here, the saline pools of that evaporitic coast. Second example I'm going to talk you through is to take you to the Jurassic coast of southern England, and particularly just one stretch of that coast between Durdle Cove, be known to many of you, and in the far distance here, Lulworth Cove, which is shown in the middle, and Stair Hole, where a feature called the Lulworth Crumple exists. This is a spectacular coast full of enigmatic structures, many of which have perplexed geologists through the last 2 centuries. So let me show you one example. This is Durdle Cove, as it is today. This is 1902 and Rowe's description of the cove, and he was really perplexed here because there were older rocks lying above younger rocks, and the micraster evolutionary trend was thrown by this particular section. That particular surface through there is one of a number of surfaces that Rowe highlighted in this vertical limb of a monocline that runs through the area, and it's cut by a series of thrust faults which occur in a triangular zone, tri-shear zone, the lowest angle of which is the one that took the older sequences over the younger and explained Rowe's original observations. That is this feature here in Bat's Head, and you can see the conjugate patterns of deformation. Now, to put this into a proper regional context, we need to look not only along strike, but also into the subsurface. Here's the Lulworth Crumple, again, known to most of us in this room, I'm sure. These 2 asymmetric folds facing inland, sitting at the eastern end of Stair Hole, close to Lulworth Cove. Now let's look in the subsurface. Here is a seismic line running south to north, and it illustrates the main fault geometries with, in this case, the Weymouth anticline, town of that name, sitting in the core of that anticline. Now what we're able to do is to take the field exposures and integrate them with the seismic data and the subsurface well control. And when one does so, we come up with this cross-section. Here is the main Purbeck disturbance. There is the triangular zone of deformation, triangular zone of shear, and that is where the Lulworth Crumple with its 2 folds sit. Effectively, this side of the fault was originally a normal fault down the way, and then pushed back up to form a compressional structure subsequently, with the thrusts affecting what were the chalk sequences that were previously unaffected by the earlier extension. We can now place those original enigmatic structures into their regional context. And it's not just there. We can go to other parts of the British Isles. Flamborough Head, the chalk, the headland goes out into the sea because it is harder. It's an unusual rock lithology that has controlled the landscape. If we look at the subsurface beneath, absolutely spectacular structural geology. Flamborough Head sits in this position in here and represents a former normal fault, then deformed in compression to create a large anticline, which is the Cleveland Dome, the whole of the Cleveland Basin. So any of us that are wondering why the Jurassic is at exposure at Whitby and Scarborough, it's because of this fault reactivating and the hanging wall to it being pushed back up. And look at the way in which the lower Cretaceous sequences and the chalk are then deformed and tilted as a result. The seismic data that we can now look at, courtesy of spec companies and seismic, proprietary seismic shot by oil companies, is phenomenal. This is, again, another one of these large extensional faults reactivated in compression at least twice. Beautiful steers, beautiful geometries. This is an arrowhead geometry as a series of normal faults have reactivated in compression. Here's an example from the southern North Sea, showing the broad deformation above these faults, uninterpreted on the left, interpreted on the right, with the extensional faults that have reactivated with this broad arch. That allows us to map the subsurface over large areas now. Here is that broad anticline that's been created by the folding. We can also restore the sections back through time. We can see how this got to be as it is today through geological time. So what I've done in this instance is to take the chalk reflector, flatten it, and you can see how the basin looked prior to this early Cenozoic compression. This is how it looked. It was stepping down. The cooler colours are deep or thick. The cooler colours are warm or shallow. We see the overall gradient down into the basin. And as this deformation took place, some of those older sequences start to fracture. This is the big fold. And then these are the faults that have reactivated, compartmentalized that particular fold. This is a time slice through the Earth. It's a bit like seeing a body scan and then horizontally slicing it. There is the large fold that can be mapped. Here are all the faults, again, that can be mapped within this particular sequence. The geometry of this particular feature can be mapped every 10 meters to 12 meters over a distance of several hundreds of kilometers in both directions. There's an unparalleled opportunity here to understand the subsurface and develop and link and extend what we know about stratigraphy, structural geology and sedimentology from onshore. And to finish, it would be remiss of me not to talk about the British Isles and William Smith's original map. The oldest rocks are up here in Lewis. The youngest rocks are beneath our feet in London. Britain has been tilted down to the southwest. It has also been folded. We have the Weald Basin now as the Weald Anticlinorium. The Cleveland Basin is an anticline. The Wessex Basin has been inverted, as you saw before. The whole of Britain has been tilted, and we can start to quantify and measure that tilt, uplift, exhumation and erosion. Over 2 kilometres of sediment was eroded over northern parts of Scotland in the early Cenozoic as part of this process. A seismic line that runs east-west through this area spectacularly shows and records this uplift with progressive subcrop of units. So this is the early Cenozoic in the sort of brown colour. The Cretaceous chalk comes up to seabed, so does the lower Cretaceous in yellow and dark green, and in blue is the Synrift sequences of Upper Jurassic Age. We can map the subcrop now of parts of this area and also see which faults reactivated as part of this tilt and uplift. There is also a sedimentary response. Spectacular imagery of what is a prograding delta, which then gets eroded in the top and infilled during the subsequent transgression. This is an image on that surface highlighting the dendritic drainage pattern that was created 55 million years ago across the North Sea that would otherwise not be possible to even contemplate was there. So what are the economic and societal consequences of this? Well, of course, we can identify prospective traps for oil and gas much better, more accurately. And in fact, one of the examples I showed you was the Cygnus field, the 6th largest gas field ever discovered, only rediscovered effectively 5 years ago. The first well drilled through it was considered to be dry. But now with better imagery and better geological understanding, Gas de France, Now Energy, have taken that through and it will be producing gas shortly. The second thing is you can evaluate and select potential safe sites for storage in the subsurface, be those for gas storage, for energy, or potentially for carbon sequestration. Where do you put the CO2 safely in the subsurface, or not? One needs to know which faults are likely to leak, which come to the surface, which units come to subcrop the seabed. It's really important to do the forensic geoscience behind that. And finally, what I hope I've been able to demonstrate, it suggests that the effects of early Cenozoic deformation on the British Isles, both onshore, offshore, and in the subsurface, not only fold, cause basin inversion, but also, importantly, reactivate faults, the effects of which compartmentalise the subsurface, and controversially here, if we think about the geology, might make shale gas extraction less likely in the British Isles. Be interested in Hugh's view here. We may be 55 million years too late for the shale gas bonanza in the UK. So in conclusion, what I hope I've been able to do is to show that the development of geophysical methods over the last 50 years has enabled really high fidelity imaging of the subsurface. Why is that important? Well, one, it helps, of course, in the economic prospectivity of the UK. But also, it does afford us a unique academic opportunity, unparalleled, I think, to investigate Earth processes back through the geological record. And in particular, as I hope I've shown here, it extends our understanding of the tectonic and stratigraphic development of northwestern Europe beyond our coasts and beneath our feet. Thank you very much.
Thank you, John. We've got time for 2 or 3 questions, if anyone would like.